This chapter closes with the question the whole course keeps returning to: add two independent continuous random variables, and what is the density of the sum? In this video, the discrete convolution of Chapter 7 ripens into an integral. For independent variables, the density of a sum is the convolution of the densities. We run that integral 3 times. 2 uniforms fold into a triangle, 2 exponentials into an Erlang, 2 Gaussians into another Gaussian, and then we skip the integral entirely. Under the moment-generating function, sums become products. Last video left us with a factored joint. For independent x and y, the joint density is the product of the marginals. Here's what that purchase buys. Form the sum, w equals x plus y, a new random variable. What is its density? The claim: the density of w is the convolution of the two marginal densities. For each target value w, integrate fx of u times fy of w minus u over every u. Every way of splitting w into two pieces gets weighed, and the roles of x and y can be swapped without changing the answer. When we convolved PMFs, we did exactly this with masses. The PMF of a sum collected px of m times py of k minus m over all m. Replace masses by densities and the sum by an integral, and it is the same sliding machine, gone continuous. To prove it, go through the CDF. The probability that w is at most w is the probability that the pair xy lands in the half-plane below the line u plus v equals w. Independence factors the joint density, so the inner integral runs the density of y up to w minus u, and that is a value of the CDF of y. Now differentiate with respect to w, sliding the derivative under the integral. Each CDF of y becomes a density of y, and what remains is exactly the convolution. Claim proved, the fundamental theorem of calculus, used judiciously. Now run the integral once and watch it happen. Draw two numbers independently from the unit interval, each uniform, two flat rectangles of height 1. What is the density of their sum? Convolution has a picture. Mirror one rectangle, then slide it across the other. At each position w, the density of the sum is the area where the two windows overlap. For w between 0 and 1, the windows overlap on an interval of length exactly w. The overlap grows and the density rises linearly, f of w equals w. Past 1, the sliding window begins to leave the other side. The overlap shrinks at the same rate it grew, and the density falls, 2 minus w hitting 0 at 2. Flat plus flat equals triangle. Sums near 1 can be assembled in the most ways, sums near 0 or 2 in almost none. And you have met this shape before. The total of 2 dice climbed bar by bar to 7, then fell away symmetrically. That staircase was this triangle, sampled at the integers, the discrete twin, resolved into a continuum. 2 more sums from the notes, each carrying its own lesson. First, add 2 independent exponential waiting times, rate lambda each. For w at least 0, the convolution runs u from 0 to w, and something pleasant happens inside. E to the minus lambda times w minus u times e to the minus lambda u multiplies to e to the minus lambda w. The integration variable cancels. The integrand is flat, so the integral simply measures the length of the interval, and the density is lambda squared times w times e to the minus lambda w. That is the Erlang distribution with parameter 2 straight out of the gallery of densities, now derived, and it reads naturally. The sum of 2 exponential weights is the weight for the second arrival. Second, add 2 independent standard Gaussians. The convolution multiplies 2 bells. Complete the square in the exponent, and the integrand splits in e to the minus w squared over 4 times a Gaussian density centered at w over 2. A Gaussian density integrates to 1, the same trick that tamed the bell curve's integral. What survives is 1 over the square root of 4 pi times e to the minus w squared over 4, a Gaussian with mean 0 and variance 2. Gaussian plus Gaussian stays Gaussian. In general, the means add and the variances add. Each of those answers cost 1 integral. This chapter closes with the shortcut. Sums become products. The same banner the discrete chapter flew, and the same trick underneath. Take the moment-generating function of the sum. E to the sw splits into e to the sx times e to the sy, and independence factors the expectation of the product. The MGF of a sum is the product of the MGFs. We built this transform when we introduced moment-generating functions. This is the moment it earns its keep. Rerun the Gaussian sum now with arbitrary parameters. The MGF of each Gaussian is an exponential in S, with its mean on the linear term and its variance on the square. Multiply the two, and the exponents simply add m1 plus m2 on S, sigma 1 squared plus sigma 2 squared on S squared over 2. That is a Gaussian MGF with the summed mean and the summed variance, the general fact in 2 lines, no convolution in sight. The key idea of this video: for independent variables, densities convolve and transforms multiply. Next up is the final chapter, sums of many variables, and the types of convergence that govern them.